Gravity is the fundamental force of attraction between objects with mass. It's what keeps us on Earth, the Moon in orbit, and galaxies bound together. Sir Isaac Newton's law of universal gravitation describes it as a force proportional to the masses of the objects and inversely proportional to the square of the distance between them. F equals g times m1 m2 over r squared, where g is the gravitational constant, approximately 6.674 times 10 to the power of negative 11 cubic meters per kilogram per second squared. While Newton described gravity as a force, Albert Einstein's theory of general relativity offers a more accurate picture. Einstein proposed that gravity isn't a force at all, but rather a curvature of spacetime caused by mass and energy. Massive objects warp the fabric of spacetime, and other objects follow the curves created by this warping. Imagine a bowling ball placed on a trampoline. It creates a dip, causing objects rolling nearby to curve towards it. This is analogous to how massive objects warp spacetime. Objects then follow the straightest path, called a geodesic, in this curved geometry. We perceive this as gravity. This explains phenomena like gravitational lensing and the precession of Mercury's orbit. General relativity predicted that accelerating massive objects create ripples in spacetime called gravitational waves. These waves carry energy away from their source and travel at the speed of light. When two black holes spiral toward each other and merge, they create intense gravitational waves that distort spacetime itself. The waves propagate outward from the merger, stretching and compressing spacetime as they travel through the universe. In 2015, the LIGO and Virgo detectors in the United States and Italy detected these waves for the first time, from the merger of two black holes over 1 billion light-years away. This groundbreaking detection confirmed Einstein's predictions and opened gravitational wave astronomy, giving us a new way to observe the universe's most violent events. Gravitational wave astronomy is a rapidly growing field that has transformed our understanding of the universe. As of 2026, over 100 gravitational wave events have been cataloged, including spectacular black hole mergers and neutron-star mergers that release enormous amounts of energy. The global network of detectors has expanded with the addition of the Kagra detector in Japan, joining LIGO and Virgo to create a more complete picture of gravitational waves from across the universe. Looking ahead, NASA's LISA mission will detect low-frequency gravitational waves from supermassive black hole mergers, opening new windows into the most massive events in the universe. While general relativity has been extensively tested and confirmed for known matter, there are still mysteries surrounding gravity. Observations suggest the existence of dark matter, which makes up 26% of the universe's mass energy and influences gravity, but doesn't interact with light. Dark matter is invisible mass that affects gravitational forces. Evidence comes from galaxy rotation curves, which remain flat even at large distances, suggesting more mass than visible matter alone. Dark energy, making up 68% of the universe, drives the accelerating expansion of the cosmos and affects gravity on the largest scales. This mysterious force counteracts gravity's pull. Together, ordinary matter accounts for just 5% of the universe. Dark matter and dark energy dominate, but their nature remains unknown, challenging our current understanding of gravity. One of the biggest challenges in physics is reconciling general relativity with quantum mechanics. General relativity describes gravity as the curvature of spacetime, working perfectly for large-scale phenomena like planets and galaxies. Quantum mechanics, however, governs the behavior of particles at the smallest scales, where uncertainty and probability rule. But these two theories are fundamentally incompatible. This incompatibility becomes critical in extreme conditions like black holes or the Big Bang, where both quantum effects and strong gravity are present. Quantum gravity research aims to develop a unified theory that combines these frameworks. Several approaches are being explored. String theory proposes that fundamental particles are actually tiny vibrating strings, with different vibration modes creating different particles. Loop quantum gravity takes a different approach, suggesting that spacetime itself is quantized into discrete loops, rather than being continuous. Other approaches include the holographic principle, which suggests that the information in a volume of space can be described by a theory on its boundary. Despite decades of research, a complete unified theory of quantum gravity remains elusive, but this quest continues to drive fundamental physics forward. Future of gravity research holds tremendous promise. Building on current discoveries, scientists will continue observing gravitational waves, advance quantum gravity theories, and conduct experiments testing general relativity in the most extreme conditions imaginable. Gravitational wave observations will expand dramatically with upgraded detectors and new facilities. By 2030, we may detect thousands of events each year, opening new windows into cosmic phenomena like black hole and neutron star mergers. Quantum gravity research will push boundaries, seeking to unify Einstein's general relativity with quantum mechanics. Theories like string theory and loop quantum gravity may finally reconcile these fundamental frameworks. Testing general relativity in extreme conditions will continue, probing its predictions near black holes, during cosmic mergers, and in the early universe. Any deviations could reveal new physics beyond our current understanding. The upcoming LISA mission represents a major leap forward. This space-based observatory will detect gravitational waves at much lower frequencies, mapping the distribution of dark matter throughout the universe and testing general relativity with unprecedented precision. Together, these advancements will deepen our understanding of gravity as the fundamental force shaping our universe, from the smallest quantum scales to the vast cosmic structures we observe today.